All right, so good afternoon, everyone. Today we keep discussing star partitions, which was the topic of last class. So to remind you all, these past two classes, we have been discussing how to generalize the graph isomorphism algorithm that we saw last week to graphs whose eigenvalues could have larger multiplicities, bigger than one, right? And then I introduced last class this notion of a star partition, which is, well, you look at the, oops, I just disappeared. Now I am back. Which is, well, you look at the vertex set of your graph, and you partition this vertex set into some subsets, all right? I'm also assuming my the spectral decomposition of my adjacency matrix is given by this sum, going from 1 to m. So m is the same. This is not just a coincidence. I truly want my partition to have the same number of distinct eigenvalues. And not only that, well, the first thing that I need that the size of each one of those vertex sets to actually be equal to the dimension of the theta r eigenspace, which I will be denoting by this capital theta. All right, capital theta r. This is the little theta r eigenspace. Right. So, but not only I want that, I also want that a basis for my theta r eigenspace that a basis is found upon projecting the characteristic vectors of the vertices in each one of the VR onto the eigenspace. And what we discussed last class is that, well, or at least I introduced these star partitions. And what was the drawing? We kind of had the drawing, so let me go back to the drawing, Spectral 6. So this was the picture that I wanted you to have in mind, which is, well, this sort of basically you have this big matrix of eigenvectors, right? And then each one of the eigenvectors, so the first eigenvectors are coming from the first block of the first projector, and then the next set of eigenvectors is coming from that set of that same block from another eigenspace and so on, right? So we have this, this was the picture, right? So it's basically this columns here are a basis for this eigenspace, and then the next block of columns are a basis for the next eigenspace and so on, right? So this was what we introduced. And then we discussed several things about this partitions last class. For example, I showed that every graph has at least one star partition, because we can very interestingly write the product of the determinant in this nice, fun way. I mentioned how the star partitions could be used for a graph isomorphism algorithm, but then we decided not to, or at least I decided not to pursue that direction, and I decided to actually show more results about star partitions without the goal of using those partitions to decide isomorphism. And today we will see some more nice results. In particular, we will see, for example, an alternative proof that a star partition exists, a proof that perhaps you will prefer. But let's go. In the end of last class, I also defined this another kind of partition called the polynomial partition. And this polynomial partition is defined, well, if I get my vertex set of my graph, and I have V1 all the way up to Vm, this is going to be called a polynomial partition. Okay, if whenever I remove each one of these things, and then I look at the adjacency matrix of these graphs, theta r is no longer eigenvalue. And what I was intending to do in the end of last class was to show that polynomial partitions correspond to star partitions, and then there was a lemma. The lemma contained a mistake. Now it's been fixed. We will see the lemma, and we will see how this lemma can be used to prove this result. All right. So the result is that polynomial partition, something is a polynomial partition if and only if it is also a star partition. So there is a sort of correspondence between removing vertices and deleting eigenvalues and finding an eigenbasis within coming from projections of the vertices of the vectors of those vertices onto the eigenspace. All right, so let's go for it. Again, I will be using capital theta to denote the theta R eigenspace. And this lemma, which is quite interesting, quite important, says that if you have a partition and the dimension is correct, meaning if the size of the vertex of this vertex sets are exactly the dimension of the theta R eigenspaces, then this thing is a star partition if and only if we have that this intersection is trivial. All right, so these are two subspaces. This is the theta R eigenspace, and this is the span of the vertices outside of the VR. All right, and then of course, because these are subspaces, they always contain the vector 0. But I'm saying that if this is true, if this intersection is equal to the vector 0 for all R, then this is a star partition. All right. So this is an if and only if. Let's start assuming that this is a star partition. Let's prove that this intersection is always equal to the 0 vector. Okay, so how do we do that? Well, I will fix an R. All right, any index is fine. I will not need to use all of them at the same time. I can simply look at one of them and I will obtain my result. And assume that the vector x lies in the intersection of these two subspaces. So what I want is to show that x is the 0 vector. All right. So I'm assuming that x is both an eigenvector, meaning ax is theta rx. Note that this is equivalent to saying that E sub r x is equal to x. Right? So this is a projection onto an eigenspace. To say that the vector belongs to the eigenspace is the same thing as to say that the projection does not change it. Right? The column space of the projection is the eigenspace, and E sub r times x is in the in this column space and always fine. Okay, I can write x in terms of a basis for the eigenspace. I can write E sub r in terms of the same basis, and things will remain. Is this clear to everyone? Yes. Okay. Now, the other thing that I want x to be in the span of this thing. So x is a vector. I can partition these entries into v1, v2, all the way up to vm. Okay? And what I'm saying is that in the, let me make this bigger. Come here. So I have that x is a vector, right? And here I have the entries corresponding to v1, v2, vr, vm. And what I'm saying is that x is in the span of these characteristic vectors that lie outside of vr. So I'm saying that these entries here are 0 in this block corresponding to vr. All right? So this is exactly what I am saying. So at the same time, well, I have exactly this. So x is an eigenvector, and the inner product of x with any one of the characteristic vectors of the vertices in VR is equal to 0. right? So this is a B here is a vector that has a bunch of zeros, has a 1 here, and a bunch of zeros. And these are the entries corresponding to VR. So of course, when I take the unit product of this vector with x, the result is 0, right? So I have that 0 is equal to x transpose E sub B. And now because x is invariant, I can multiply x by the projection, nothing changes. So I'm replacing x by E sub r times x. Now I am, of course, applying the transpose in this matrix product by a vector. And I'm using the amazing fact that this projection is a symmetric matrix. And now I have that x transpose times this is equal to 0. But why is this a sort of, not a contradiction, that's not what I wanted to say. Why? So what does this tell me? Well, x belongs to the eigenspace, right? The theta r eigenspace, and E sub r times E sub b is in the basis for the eigenspace, So this does not allow x to be non-zero, because if x is non-zero, there is clearly a contradiction here, right? Because x will be, and this is true for all b, right? So this cannot be true for all b. X cannot be orthogonal to a basis of the space it lives in, unless, of course, x is equal to 0, which is what we wanted to show. All right, any questions? All right. Now, for the other direction, I am assuming that this intersection is the 0 vector for all r, and I want to show that this is a star partition. So how do we do that? So I will consider, oh, there is a question. Yes. X transpose EB 0 because X is in the span of the eigenvectors, not in VR. No, because X is here in the span of these guys. So X is of this form. So not eigenvectors, characteristic vectors. That's probably what you meant, right? Yes. Now, for the other direction, it follows from hypothesis that there is a basis for the space obtained from joining a basis of the theta eigenspace and each one of these guys. So what's happening here? The intersection here is the 0 vector. Now this is a subspace of dimension VR. The dimension is VR. This is a subspace of dimension V minus VR. So any set of vectors from this united with a set of vectors from this, any linearly independent vectors from this with linearly independent vectors from this will be a linearly independent set. Why? Because, well, if the set of vectors is linearly independent in the eigenspace, there is no trivial linear combination which is equal to 0. And then I get another set of vectors here for which there is no trivial linear combination which is equal to 0. And I get all of them together. And if suddenly there is a non-trivial linear combination which is equal to 0, it means that I can move. So imagine that I have here alpha 1 v1 plus alpha 2 v2 plus dot 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 plus say that this dimension here is equal to d, whatever, alpha d vd plus beta 1 I don't know, u1 plus dot 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 plus beta n minus d u n minus d. Okay, now this lie in the theta r eigenspace, and this lie in the span, okay, of the E sub A in VR, not in VR. Now, if this thing is equal to 0, I can get these guys, move to the other side, and then I have that this thing is equal to minus these guys. So there is an intersection, but then what's happening is there is no intersection. Intersection is the 0 vector. So if I have something in the eigenspace equal to something on the other, these things must be 0 themselves. So this must be 0, and this must be 0. But then these are linearly independent vectors in each one of the spaces, so all of the coefficients must be 0. This is quite interesting. This is telling me that if I get a basis for my theta r eigenspace, basis for theta r, and I unite this basis with a basis for the other thing, which is basically the E sub A for A not in VR, this forms a basis for this space, because these are all linearly independent, and I have the right quantity of vectors, because the sizes match. A basis for the theta r eigenspace has precisely this many vectors. I have a bunch of vectors, and the quantities match. So I can obtain a basis for the entire space, joining a basis for the theta r eigenspace, and a basis for the other. Now this means that there is also another basis for the space, which is formed by taking the orthogonal things of these. So now I pick a basis for the orthogonal complement of the theta r eigenspace, and I get E sub A now with a belonging to VR. Now, why are these things also, so it's clear that A have the right number. Why are these things also linearly independent?
In the first part, they are orthogonal. So when you take the orthogonal basis of theta r orthogonal, it becomes the thing that was on the left on the top.
Not necessarily true, no. Not equal, right? So this subspace is not necessarily equal to this. So what is the picture here? For example, if we are in R2, okay, I'm gonna write two subspaces. One is this subspace, and the other is this subspace, for example. Right? So these two subspaces intersect in the 0 vector. Why, if I take now the orthogonals of both, I still have two bases, right? See. So this is playing the role of the theta r. This is the E sub A naught in VR. This is theta r orthogonal. This is E sub A in VR. See, it's not necessarily the case that this guy here is equal to this guy here. But why do I keep orthogonality? Not orthogonality, but 0 intersection.
you have a vector at the intersection, then you pick this vector and you multiply by a vector at theta r. Since this vector is in the complement of theta r, then in the orthogonal space of theta r, this product would be 0. But then you multiply this vector to e sub a, and it will also be 0. So this vector is not in the basis of theta r, neither in the span of e sub a, but it is a non-zero vector. So it would not be in the whole space.
So imagine that this contains a vector, I don't know, v, right? So now, okay, so v belongs to this thing, but this is a basis as well, right? So supposedly there should be a way of writing v in terms of this basis, but how can this work? So if I project v onto the theta r eigenspace, the result has to be 0, because v belongs to the orthogonal complement of the theta eigenspace. And if I project v onto this guys, the result should also be 0, because v belongs to their orthogonal complement, right? So v must be the 0 vector. When I write this vector in terms of this basis, I conclude that the only thing that works is the 0 vector. Very good. So this basis is also this is also a basis. So this intersection here is also going to be sorry, I meant to say now intersection, right? So for this to make sense, pick v in the intersection, right? So now I know that there is a basis for this space, which is the union of these two bases. So then this means that the theta r eigenspace is generated by the vectors obtained from applying e sub r to this basis. Now I have a bunch of vectors, v1 all the way up to v, I don't know, k, and these are bases for the theta r eigenspace, and I have, sorry, the orthogonal complement, and I have the e sub a belonging to vr, right? So these two sets, they form a basis for the space. Now, any vector is written in terms of these guys, right? And then the theta r eigenspace is generated by things of the form e sub r times v for all v, vector of the space, right? So these are all possible things. Now, this guy here, written in terms of this basis, these guys will die when I apply e sub r to them. The only thing that remains is e sub r applied to these guys. And I'm gonna sneeze now. Much better. And e sub r applied to these guys. So this will generate the theta r eigenspace. So the conclusion here is that e sub r applied to e sub a for a belonging to vr generate the theta r eigenspace. Now this is true for all r. And there was an exercise last class that said, very important exercise, that something's a star partition if and only if for all r these guys are linearly independent, which is if and only if for all r these vectors span or generate the eigenspace. And we are done. All right. So we have this very, very nice lemma. Now let me ask you, how can this lemma be used to show that a star partition exists? Right? How? How can I use this lemma? So the idea is the following. So I think this was also actually a question last class, and I think that I answered this wrong, and I realized that this was wrong when I was preparing today's lecture. So imagine that I have a set S, subset of the vertex set, so that E sub R applied at E sub A for all A belonging to S are linearly, independent, or actually form a basis, for theta R. I want to argue that I can extend this set, to a star partition, meaning there is a star partition that will contain this guy as the V sub R cell of the partition. I think this was a question last class. Someone asked me if whenever you find this, you can extend to a star partition, and I said no, but actually it's yes, you can. So how does this work? Look at the E sub R matrix, okay? Look at the block that corresponds to this S. Say these are the first, but it could be any block here in the matrix, and of course it doesn't need to be a continuous set of columns, right? It could be spaced by some holes, but imagine this is the block, right? Now, because these vectors form a basis, these column vectors are linearly independent. So of course, this block here has full rank. What do I mean by that? I mean that the rank of this block is this obvious? It's not immediate that this block has full rank. So let me explain that. So this thing here is so when I multiply E sub R by E sub R, the result is E sub R, which means that and this thing, an entry here, and this block, I have this matrix times this matrix is equal to itself, right? Now I'm looking at this block here. An entry here is going to come from this row, right? And this column. But these are, of course, so this row times this column is going to be equal to this entry. And this row is also equal to this row. So this is the gram matrix of the first S columns. Right? What does it mean to be the gram matrix of the first S columns? It means that each one of the entries here, entry ij, is equal to the inner product of the ith column with the jth column. So basically, if let's say, I don't know, P is the matrix that contains only the first columns of the projector, right? So P is this matrix here. This is matrix P, right? Then what's happening here is that this guy is P transpose times P. right? And what can I, and why this allows me to, and these has the same eigenvalues as PP transpose, except possibly for 0, except possibly for 0. So what's happening here? Well, if I get P transpose times P times V is equal to theta times V, then PP transpose P times V is equal to theta times PV. So as long as this guy is not 0, I get that this thing here is not 0, and I get that this guy is also an eigenvalue for this matrix, and vice versa. Now, this matrix here has dimension of theta r eigenvalues equal to 1. So this matrix has those many eigenvalues, but this matrix has size precisely this dimension. This matrix is S by S. There's something off. Oh, this matrix doesn't have these eigenvalues equal to 1, but they're different than 0. Sorry, they're different than 0. And then, of course, these will be the same eigenvalues for this matrix. I'm good now. So yes, so this matrix has full rank, this block here. Now, let, I don't know, Q be a matrix of eigenvectors to the space. Okay? I have a bunch of vectors, and I'm assuming, of course, these first ones here correspond to this isobar that I'm looking, right? So these are the eigenvectors multiplied by some numbers on the columns and some numbers on the rows. But what I want to say is that that block is basically here. Okay? And this block has full rank, so these columns are linearly independent. Of course, right? I'm good. But now, I want to look this block here. And I want to argue, so this block has determinant different than 0. And I want to argue that this block also has determinant different than 0. So in order to do that, I need to show that these columns here within the block are linearly independent. Now I go back to the lemma. The lemma said that I have no vector but for the 0 vector, which is in the span of the things outside of VR, and also in the theta r eigenspace. Now these guys belong to the span of the things outside of VR, because these are the vectors VR. So this is everything outside. These are the rows corresponding to VR, and these are the rows outside. Now, what happens if I get this block here? So call this block M. Okay, I get M. So what happens if I get this block and I apply it to a vector and I get 0? What happens if m times u is equal to 0? What is the problem here? So what I want to put m followed by some 0 matrix, perhaps the other way around. Some 0 matrix followed by m multiplied by a long vector here with the zeros, u, and the result is 0. So this is the same thing as saying that mu is equal to 0, right? Well, if this vector is non-zero, it means that this vector is going to be orthogonal to all of these columns. So it must belong to the theta r eigenspace because it's orthogonal to all eigenvectors of the graph which are not in the theta r eigenspace. So at the same time, I will have something which is non-zero, belongs to the theta r eigenspace, and belongs to the span of the E sub a not in VR, and that is not possible. So this thing must be 0. And so this matrix does not have a non-trivial kernel. So its determinant is non-zero. And therefore, you can apply induction. Simply, very simple. You started with a set of the vertices, you pick one, you project onto the eigenspace, it's linearly independent, it's non-zero or linearly independent. You pick another, as long as it's linearly independent, you keep going. When you can no longer continue, you have a basis for that eigenspace. Now, you go to another eigenspace, you pick a vector, projecting there, a vertex, projecting there. If it's linearly independent, you keep going, and everything should work. Because you know that whenever you finish with the basis of an eigenspace, and you have a block, the complementary block in the eigenvector matrix will have non-zero determinant. So you're free to continue. All right? So this is also another way of showing that a star basis always exists. And it's actually easy to find. Simply keep going, keep testing, projecting vectors, vertices onto eigenspaces, and as long as the thing remains linearly independent, you can keep going. Okay? All right. So this is one application of the lemma, the fact that star bases always exist. But let's see another which is our initial goal, right? So to show that any given partition, if it satisfies the property that when you remove the vertices of each cell, you kill an eigenvalue entirely. So if this property holds, then it is a star partition and vice versa. So to see that, we will be using the lemma quite heavily, actually. This is not that trivial, but it's actually quite nice. So let me erase. Do I want to erase? No, I want to simply start treating. So start assuming that you have a star partition. So I want to show that theta r is not an eigenvalue of G with V sub r removed. Okay, so simply denote A prime to be the adjacency matrix of this graph, right? And let U prime be a vector so that A prime U prime is equal to theta R U prime. So I want to show that U prime must be the zero vector, and therefore theta R is not an eigenvalue of A prime. Okay? So let U be obtained from U prime by adding zeros in the positions corresponding to the verses in VR. So what is the drawing here? Imagine that I have my matrix A of G, right? Suppose that these are the vertices corresponding to VR, and I am going to delete these vertices. So this thing here that remains is A prime. Okay? Now I am assuming that A prime, times U prime is equal to theta U prime. And I'm also defining U to be a bunch of zeros and U prime on the bottom. So what I will do now is apply A to U. Is this what I'm going to do? I think this is what I'm going to do. Yes. So, what is this? This is this block. Here I have A prime, and I'm multiplying this by 0 and U prime. Right? This is what I want to do. Yes. Let me see. Yes. So what is the result here of this multiplication? Well, I'm going to have something here, and here I'm going to have A prime U prime. So this thing is something theta U prime. So when I multiply E sub A by A times U, the result is theta E sub A transpose U. If A is not, I'm assuming A does not belong to VR. So I'm simply multiplying this vector by a characteristic vector that has zeros here. Right? So theta U is equal to zeros and theta U prime. Multiplying this red vector by this guy or by this guy gives me the same answer, right? Because the 1 is where the two vectors are equal. These two vectors are different, where here I have zeros. So this is true. Okay? Any questions so far? What do I want? Let me move this thing. Hold on a second. How can I move this? Oh, great. So I probably want to move this up. Very good. So this is the conclusion. E sub A transpose A minus theta I times U is equal to 0. So this vector is orthogonal, and this is true for all A, right? Outside of VR. So this is spanned by E sub B belonging to VR. Right? It lies in the orthogonal complement of these guys. Now, on the other hand, if we have that AX is equal to theta X, then X transpose AU is equal to theta X transpose U. And therefore, this is going to be orthogonal to the theta eigenspace. Right? So if I get AX equal to theta x, and then I get AU, and I multiply this by x, this is going to be precisely equal to theta times x transpose U. This U, the U that I'm using up here. So the conclusion is that x transpose A minus theta I times U is also equal to 0 if x belongs to the theta eigenspace. So this lies in the, so this is orthogonal to the theta eigenspace. So this vector is at the same time orthogonal to the theta eigenspace and is spanned by these guys. So therefore, by the lemma, this vector must be the 0 vector. The conclusion is that A minus theta I times U is 0. So A times U is theta times U. But now there is a problem. What is the problem? U is of the form a bunch of zeros, U prime. So this is saying that U is in the theta eigenspace and is also spanned by the guys outside, which again, from the lemma, implies that U must be the 0 vector. So U prime is equal to 0. And therefore, this A prime matrix does not contain theta as an eigenvalue. All right, so this is quite the convoluted argument. It applies the lemma twice to show that there cannot be a vector satisfying this equation, unless, of course, it is the 0 vector. So this shows that if you have a star partition, then when you remove the verses of each cell, you must be killing the eigenvalue. Now, the other direction, assume that you have this equation. So what is the other direction? I want to assume that if for all r, this guy is not an eigenvalue, then the thing is a star partition. Okay? So I am picking theta r an eigenvalue of the graph. Oh, sorry. I'm writing now for the converse, of course. So here's where I am. For the converse, I'm assuming that for each r, theta r is not an eigenvalue of this thing. Now, from that very same exercise 2.7, the only thing that I need to show is that this E sub r span the theta r eigenspace for all r. So assume Ax is equal to theta r times x, and also x transpose, what do I want here? Assume Ax is equal to theta Rx, and also that x transpose E sub r, E sub a is equal to 0, maybe? Hold on a second. Yes, so equal to 0 missing here. This means that E sub r x transpose E sub a is equal to 0. So this a here is in VR, right? This means that this guy is spanned by E sub b for b not in VR, but x is an eigenvector, so E sub r x is equal to x, And so X is a vector which is 0 at the entries corresponding to VR and also satisfies this equation. Therefore, X is of the form so X is eigenvector, and X is of the form a bunch of zeros in VR, and here I have X prime. So then again, I look at my original matrix A applied at X. It's the same thing as this with A prime, applied at zeros with X prime here, and the result is A prime, well, the result is going to be some zeros, A prime, X prime, right? And then I know that I'm also assuming that this is an eigenvector, so this is also theta r times a bunch of zeros, X prime. So the conclusion is that these two things are equal, these two things are equal, and therefore X prime is an eigenvector for theta r to A prime, but by hypothesis this does not occur, so X prime must be 0, so X is 0, and we are good to go. So this is not possible, this is not possible, and we're good to go. All right. So we have, what do we have? We have this very important, nice lemma, which unfortunately I had it wrong last class, now I have it right. It is quite the useful lemma to analyze this connection between eigenvectors and verses of the graph. It allowed us to show that star partitions are the same thing as polynomial partitions, which is quite nice. But now, this is also a very nice exercise, which you guys could try. It's not supposed to be difficult. If you have a star partition, you have to show that the block of VR, which correspond to the rows and columns indexed by this thing, is actually a diagonal block. Is this true? I think this is true. Yes, this is definitely true. How do you know that? So how would you prove such a thing? Well, imagine that you have a basis of eigenvectors for the space, okay? And look at the vectors corresponding to the theta r eigenspace, and then here you have the VR, right? So what we know is that this is a square matrix of non-zero determinant, right? Now, if this is non-zero determinant, you can perform row column operations so that this matrix becomes diagonal. So perform elementary column operations so that this becomes diagonal. Now, is this making sense? Because the remaining vectors are not going to be orthogonal anymore, will they? Okay, I'm not sure if this exercise is right. Let me think about it. I will decide if it is right. If it is right, I will put this, if it's not right, then I will fix it. All right, let's move to the next topic. The combinatorial connections to star partitions. So here now I want to explore a little bit of what you can say about the combinatorics of the graph, some eigenvector applications of the star partitions, all right? So, any questions so far, up to this point? Paulo, Bruno, everything okay? Flavia? You guys are silent. Well, Emmanuel is agreeing with everything that I say, so I'm trusting him, but how about the other people without the camera? Are you following? Okay. Let's see this nice initial application. So let V1 up to Vn be a star partition, let A and B be distinct vertices in the same cell. Say that this cell is called VR. If the neighbors of both vertices outside of VR are the same, then it must be that these vectors, the eigenvalue is either -1 or 0. Okay? So what I'm saying here is I'm picking, so this is my graph, and I have V1, and I have V2, and I have V3, ... And then I'm looking at one of these VRs, all right? Then I'm picking two verses in there, two verses here, A and B. And I'm saying that the neighbors outside of here are the same. So let's say this vertex has a neighbor here, here, and here. This vertex is also the same. All right, so this is my hypothesis. And then I'm saying that this allows for only two possibilities. Either they are neighbors themselves, the eigenvalue is -1, and all of their neighbors are the same, including those within the partition, the cell they are, or they are not neighbors, the eigenvalue is 0, and all of their neighbors are the same also. Okay, so it's kind of, this is a very strong restriction. If the verses have the same neighbors outside of their cell, you already know which is the eigenvalue, and how do they look like. And in fact, so this is basically saying that well, let's see the proof first, and then we discuss. So this is the eigenvector equation. All right. What do I mean by that? So this is equal. So A times E sub r is equal to theta r E sub r. All right. Is this easy? Flavia, if you had to prove this now, how would you start? Or Bruno, you're a good one, Bruno. How would you prove this now? Why is this true? Well, for example, one of the ways you could prove this is by writing the spectral decomposition of A and multiplying this sum by certain E sub r. So this thing here times E sub s, E sub r, E sub s is equal to 0 whenever r is different than s. So a bunch of things will cancel, will 0, and the only thing that survives is theta s times theta s squared, but theta s squared is theta s. All right? So this guy is equal to this guy here. And now, also, if I multiply from the other side, the same thing is true, of course. If I multiply theta s from this side, nothing changes. So I still get that A times E sub r is E sub r times A. But now I'm using this thing here. A times E sub A is the sum of the neighbors of A. Right? This is the definition of the adjacency matrix. So that's it. This is what I get, right? So this is simply the eigenvector equation applied at a particular eigenspace. It's quite a useful thing. We have that this is equal to this. So now what I'm going to do, I'm going to perform the operation theta r multiplied by I sub r I sub a minus I sub r I sub b. Recall that A and B are the two verses that I am looking at, which are in the same cell. These are A and B. So when I perform this thing here, what do I get? Well, I get the sum of the neighbors of A, I sub r, I sub c, minus the sum of the neighbors of B, I sub r, I sub c. Now they have the same neighbors outside. So this thing here becomes the sum of the C neighbor from A, neighbor from B, and C not in VR of I sub r, I sub c minus I sub r, I sub c, which is 0, of course. So the part outside of VR cancels. And what is left here is the sum of I sub r, C neighbor from A, C belongs to VR, minus the sum, I sub r, I sub c, C neighbor from B, C belonging to VR. And what is the problem here? These vectors are linearly independent. So there cannot be a non-trivial linear combination of these things equal to 0. Because the vectors in here are all linearly independent. Right? I know, of course, that this thing is equal to 0. Oops. No, sorry, what do I have? I have that theta r I sub r I sub a minus theta r I sub b is equal to this thing. So this will be a non-trivial linear, I move everything to the left, and then I will have a non-trivial linear combination of these things equal to 0. And that is a problem, right? Unless, of course, one of the possibilities, this guy is 0. Is this making any sense? So let me write this in the right way. So what do I have here? I have theta r I sub r I sub a minus theta r I sub r I sub b minus the sum of the C neighbors from A, C belongs to VR, I sub r, I sub c. Let me use now another index. Let's say D neighbors from B, D belongs to V sub r, I sub d equal to 0. So these vectors here are all projections onto the theta r eigenspace of E sub u with u belonging to VR. And these are linearly independent because this is a star partition after all. So this is a linear combination equal to 0. So the numbers, the coefficients multiplying each one of these things must be equal to 0. So who is multiplying I sub r, I sub a? Well, theta r for sure, but I sub r, I sub a could appear somewhere else. Where? Amongst the neighbors of B. There could or could not be amongst these neighbors A. A could be a neighbor of B. And if it is, if A is a neighbor of B, then there is another thing here, and what multiplies this is theta r plus 1. And if A is not a neighbor from B, then this guy is not here. So basically I have two options. Either A is a neighbor of B, in which case theta r is minus 1, or A is not a neighbor from B, in which case theta r is 0. Which is exactly the two conditions of the lemma. And this one here follows immediately if you realize that all coefficients must be equal to 0. So whichever neighbor appears here must also appear here, so that this minus 1 cancels with this plus. And everything becomes the trivial linear combination. So this is yet another application of the fact that if you get linear independent vectors and they sum to 0, all of the coefficients must be equal to 0. So this is quite nice. This is already somehow connecting combinatorics and eigenvectors in a sense, right? It's looking at a star partition and I'm finding information about the eigenvalues. Of course, I had to assume something, but that's fine. That's okay. A similar analysis, yes.
There is an example where this happens.
Yes.
I mean, an easy example.
That you have two verses in the same star cell, and that this is true.
Yep.
Let me think.
For example, P3.
Yes.
No.
Not P3, but almost. P3 is my favorite example. So probably this graph. Zero has multiplicity 2. Okay. One eigenvector is plus 1, minus 1, 0, 0. And the other eigenvector is plus 1, 0, minus 2. Looks good, looks good. Yes. So 0 has multiplicity 2, and I am pretty sure this versus form a basis for the 0 eigenspace. So if this is A and B, then E sub 0, E sub A, and E sub 0, E sub B are bases for the 0 eigenspace. All right, and if there is a connection here, so these are, so they're not neighbors, right? And good. And if the graph looks like this, then what do I have? I have plus 1, -1. I want -1 to be an eigenvector, right? Yeah, so 0 again, and 0. So this is an eigenvector for -1, right? Because the sum of the neighbors is -1 times the value in there. And also, here, I put +1, +1. So I want the sum of the neighbors to be -1 times what is in there. Looks good?
I guess that in this case, -1 do not have multiplicity 2.
It does. It just created 2 eigenvectors.
At the right, it's not an eigenvector of.
You're right. How about now? No, right?
But I guess that I used Bruno software and I saw that this graph does not have multiplicity 2 for the eigenvalue -1. But for the triangle, I guess that it works.
Without this?
Yes.
Fair enough. Looks good. Yeah. That's a good point. Okay. So yeah, so these would be 2 examples for this theorem 2.14. Okay. So basically, it was easy to create this because I'm already assuming that these 2 verses are twins, so they have the same neighbors. What this theorem is saying is that if you need only to know that they have the same neighbors outside of the classes. So this is, I want to arrive into some combinatorial consequences of these things, right? So this is quite a nice one. This exercise is also quite nice. It says that if a graph has no isolated vertex and there is a vertex in one of these cells, then it must have at least one neighbor outside of the cell. Okay, meaning if you look at the drawing, it cannot be that there is a guy here and its neighbors are all in here. It must have a neighbor at least outside of it. And it's an immediate consequence of this equation. So truly, you can use this immediately to, if you understood this equation, you're going to get that quite easily. And then you can use this information to characterize which are the star partitions of the complete bipartite graph. We saw that the complete bipartite graph has eigenvalues this, and this, with multiplicity 1, multiplicity 1, multiplicity m plus n minus 2. So by using this information, right, so you have a bunch of vectors versus here, a bunch of versus here, edges everywhere. So I'm telling you that which are the star partitions, meaning which are the verses that are going to generate this guy. Isn't this equivalent to the not existence of a connected graph with a single eigenvalue? What do you mean? There is
the affirmation that let A in VR show that A has at least one neighbor outside of. No, it's stronger.
You're good?
Yeah.
Okay.
I was thinking that this was only possible if you had a connected component and you chose only vertices inside the component to the VR.
Right. Now, another way of interpreting the theorem that we solve is that when you pick two neighbors A and B in the same VR, then the symmetric difference of their neighborhoods cannot be a subset of VR unless the eigenvalue is -1, if they are neighbors. And if they are not neighbors, the symmetric difference cannot be a subset of VR unless the eigenvalue is 0. So as a consequence, we have this very nice corollary which says that if you fix M and the eigenvalue is not 0 or -1, then there are only finitely many graphs for which the theta eigenspace has codimension M. Because what's happening here is that when you look at the graph, and here is the VR, and theta r is neither 0 nor -1. Each guy here has some neighbors outside, but another guy cannot have the same neighbors. So this guy must have a distinct set of neighbors. Now, if here there are m vertices, each one of the vertices in here is going to be determined by a subset. So in here, there are at most 2 to the m vertices. One for each possible, actually 2 to the m -1, because the empty set is not an option. So because each one of these guys, right, have a neighborhood here outside, and these neighborhoods must be different. So this graph has the total size of m plus, the definition of codimension is the n minus the dimension. N minus the dimension of the theta r eigenspace is equal to m, means that this is true. This is, if you stop to think about it, this is not something you would, well, be able to prove if you did not know about these things. This is really starting to look like the types of questions which are not easy. I mean, if I tell you how many graphs are there in which I don't know, 10 is an eigenvalue and the dimension of the eigenspace containing 10 is 3. And it could be infinitely many, who knows? But this is putting a bound. This is saying that if n minus the dimension is a number, then n is bounded by this number plus this power. All right. And the last thing that I want to talk to you guys about is about dominating sets, because this is quite the interesting topic in combinatorics. There's a lot of research being done about this parameter. So basically, a set of vertices in a graph is called dominating if everyone outside of the vertex set has at least one neighbor in it. Could have more than one, could have 2, right? Now, why is this useful? I mean, you can model several problems of the real world using dominating sets. The most famous is you want to put cameras in the hallways of a museum so that all hallways are covered by at least one camera. You want to use the smallest possible number of cameras. So this is something you could be using to formulate this problem, for example. So typically you want to find the smallest possible dominating set, because of course, if you pick all vertices form a dominating set. So this is called the domination number, the smallest possible dominating set, domination number, beta of G, typically denoted. And guess what? It is NP hard to compute it. So no. The location dominate a set is called location dominating if any vertex outside of it is uniquely determined by its non-empty neighborhood. So within there, so this guy has two neighbors, and this thing is called location dominating if there is not another one which is neighbor to the same two guys, meaning any subset here determines, which is a neighbor of someone, determines exactly who is this vector. Okay? Now, it is quite the immediate conclusion from the stuff that we were doing right before that if this is a star partition, then the complement of VR is a dominating set for all R. And if theta R is not 0 or -1, then the complement VR is actually location dominating. Well, because I just told you that for any vertex in VR, it must have at least one neighbor outside of it. And believe me or not, this is actually not that bad of a bound. It's not terrible. So this is basically saying that if you list your eigenspaces of the graph and you write their dimensions, so this has dimension d1, this has dimension dm, then the smallest possible dominating set is smaller or equal than n times dr for all r. So if you have an eigenvalue with very large multiplicity, then you are good. And there are graphs for which this bound is actually tight. And this is actually quite nice. And at least, and there is some usage in this because after all, well, this is a dominating set. So it is at least something you can start with if you want to find a dominating set. You can now greedily ask whether or not you want to remove, you can remove verses from it. Of course, this strategy cannot lead to a good algorithm, so because this is NP hard, but it is nice heuristics. Start with the eigenvalue with largest multiplicity, find the star partition, look at the complement of the cell corresponding to that eigenvalue, remove a couple vertices, see what you got. Okay, this is quite nice. And then you also have the location dominating, which is even more complicated to find typically, as long as your eigenvalue is not 0 or -1. So if you have an eigenvalue not 0 or -1, and it has large multiplicity, then you have a lot of structure. A lot of structure in your graph. And this is nice. This is the sort of questions we typically are interested in spectral graph theory. Okay? And I guess I want to finish with this lemma 2.18. I don't think I will pursue this lemma 2.19 next class and forward. So actually, no, this is already talking about this minimal dominating sets, and I don't think I will finish. So the reference that I was using to prepare this lecture is actually has a theorem about when this VRs are, sorry, the complement of the VRs are minimal dominating sets, but I don't think I will go all the way to that theorem. So next class, I will start with the section 4. All right, so I intend to finish here with this nice application of domination. Okay, star partitions apply to domination. And so what was my goal today's class? Was to teach you guys a lot of linear algebra. I mean, these trivial manipulations, not trivial, elementary manipulations with these eigenvectors, eigenvalues, and this very nice application of the dimension argument, right? With the with this very nice application of this lemma. So I truly expect that you guys appreciate and learn something today. Now, next class we start with more, let's say, basic stuff. Still talking about eigenvectors and eigenvalues. We will next class start to learn how to write an entry of this thing without computing eigenvectors. Okay? Um, that's it. I will stop here. I will put the class notes from today and my class notes on the website, everything. I will do that. Thanks for asking.